The invisible architecture of power. Unveiling the dual nature of the electric dipole. At the heart of many natural phenomena lies the electric dipole, a simple yet profound arrangement where a positive and a negative charge are locked in a permanent dance. This configuration creates a force field that reaches out into the surrounding space, influencing every other charge that enters its domain. When we look closely at the mathematical personality of this field, we discover a rare and beautiful symmetry. It is both perfectly balanced and directionally consistent. The two secret rules of the dipole field. Every force field has a set of rules it must obey. For the dipole, two specific properties stand out. First, the field is solenoidal, meaning that if you were to draw a bubble around any point in space, the amount of force flowing in exactly matches the amount flowing out. Second, the field is conservative, which means it doesn't contain any closed loops or whirlpools that could trap a particle in an infinite cycle. Because it follows these two rules, the field possesses two distinct shadows or potentials that describe its entire structure. The energy landscape. Hills and valleys. The first way to visualize this field is through its scalar potential, which we can think of as a landscape of hills and valleys. In this analogy, the positive charge of the dipole acts like a high peak, while the negative charge acts like a deep pit. Any test charge placed in this field is like a ball on this terrain, naturally wanting to roll from the heights toward the depths. The most striking feature of this landscape is that it is energy neutral over the long term. If a particle travels in a loop and returns to its starting point, it will have neither gained nor lost any energy. The hidden swirl. The vector potential. While the landscape of hills and valleys tells us about energy, the field has another hidden layer called the vector potential. Even though the field itself doesn't loop, this potential describes the intensity and concentration of the field's influence as it spreads outward. This is particularly fascinating because it bridges the gap between electricity and magnetism. This exact same mathematical pattern is what we see when we look at a tiny loop of electric current or a standard bar magnet. In the world of magnetism, this potential is actually more fundamental than the field itself. The field in motion. A living simulation. To truly understand the dipole, we must watch how it interacts with